Today we will be talking about sets. Sets can be combined with other sets. For instance, the set of University of Michigan students who have a Facebook profile and the set of UM students who have a Google Plus account are able to be combined in numerous ways. We could form the set of UM students who have a Facebook profile and Google Plus, the set of UM students who have a Facebook profile or Google Plus, the set of UM students who have a Facebook profile and not a Google Plus, and so on. Since sets can be combined in a number of ways with other sets, set identities are vital to set operation. We are going to examine the most important set identities and prove them either using a Venn diagram representing the relationship of sets or using set builder notation and logical equivalences. You can also use a membership table, but we will not be discussing that. The first law associated with set identities that we will examine is the identity law. For our real-world examples, we will let A be the set of UM students with Facebook profiles, B be the set of UM students with Google Plus accounts, C be the set of UM students with Twitter accounts, and U be the universal set of all UM students. With the Venn diagram, we see that the intersection of set A and U is A, since only the UM students with Facebook profiles are contained in A itself and part of the universal set. The union of set A and the empty set is set A, since the empty set is an element in set A. Now we will examine the domination law. With the Venn diagram, we see that the union of set A and the universal set is the universal set, since UM students with Facebook profiles and all UM students are either elements in set A or in the universal set or in both. The intersection of set A and the empty set is the empty set, since the only elements in set A that is in the empty set is the empty set itself. Next, we will look at the idempotent laws. We see that the union of set A and set A is the set itself, A. This is also true for the intersection of any set to itself. Now, here is the complementation law. The complement of set A is the UM students who do not have a Facebook profile. Hence, any element in set A is not the complement of set A. The complement of set A is set A. The negations cancel each other out, like in the multiplication of two negative numbers. For the commutative law, we have A union of B equals B union of A, and A intersection of B equals B intersection of A. You can rearrange the order of sets only when they are combined in the same way. The union of set A and set B is equivalent to the union of set B and set A. This works the same for intersections as well. For the associative laws, we are allowed to group the sets as long as they are all combined through the union or through intersections. The distributive laws are for a set to be distributed and explicitly grouped with other sets. Now the De Morgan's laws for a set are similar to the De Morgan's laws for propositions. Not A intersection of B equals not A union of not B. And not A intersection B equals not A union not B. We will use set builder notation and logical equivalences to establish the first De Morgan's law for sets. Not A intersection of B is X when X is not an element of A intersection B. The absorption laws are as following. A union of A intersection B equals A, and A intersection of A union B also equals A. We can prove this by set building notation. For the first absorption law, suppose X is an element in the set of A union A intersection B. Then X is an element of A, and X is an element of A intersection of B by definition of union. Because X is an element of A, we have proved that the left-handed side is a subset of the right-handed side. Conversely, let X be an element of A. Then by definition of intersection, X is an element of A intersection B. Therefore, X is an element of A union A intersection B by the definition of union, so the right-handed side is a subset of the left-handed side. The complement laws are the A union the complement of A equals the universal set, and A intersection of the complement of A is the null set. We have examined some of the most important set identities. These can be utilized in proving other set identities for those that are more complex and cannot be easily proved through a membership table.